Alright, this is episode 9.2, where we take a look deeper at these electron families and the shapes that they're going to make. First, a couple of pieces of language that we'll use throughout this description. All of this that we're going to write about is based on what's called the VSEPR model. VSEPR stands for Valence Shell Electron Pair Repulsion Model. And what that says is that valence electrons repel one another. Just like these balloons right here, when you tie them together, they want to get as far away from each other as possible. Well, it's the same thing with electrons. Electrons inside of a molecule, they just want to get as far away from each other as possible because they're both negative. And like charges repel. So to describe where these electrons are, we call them electron domains. And an electron domain is an area or a space where bonded or non-bonded electrons reside. And here's a couple of examples. So these are just bonded portions of different molecules. So here's CH. This is called a bonded electron domain because carbon and hydrogen are bonded to one another. Here's another example of a bonded electron domain because we have carbon and oxygen double bonded together. So it can be a single, double, or triple bond. We just call that a bonded domain. Here's a bonded domain. Here's a bonded domain. Now, if we have unshared pairs of electrons, little dots that aren't connected to something else, we call it a non-bonded electron domain. So there's bonded electron domains and non-bonded electron domains, and those decide inside of the family what the molecular shapes are going to be. So be able to count them, how many bonded domains, how many non-bonded domains there are, and then know the electron domain geometry, and then you can find what's called the molecular geometry, or the part of the family of each setup of shared and unshared electrons that tells you what the bond angles are. All right, let's get into the deep part of it now. Let's get into the pieces that tell us the molecular geometries and therefore the shape of all kinds of different molecules. So you'll need to take your notebook and you'll need a new page for this because you want to turn your paper sideways like this. So even if you only have a few notes written down on this page, take a second right now and go to a new page and set it up sideways. So we need a sideways page like this. And then at the very top of the page, we want to make 1, 2, 3, 4, 5, 6 different columns, just like I have. And you can make little lines coming down these columns like this. And I'll give you just a second to set it up, or pause the video now to make sure that you can set it up. Alright, so let's start with the family of 2 electron domains. So 2 electron domains would have the name that we learned last time called linear right here. And the electron domain geometry has 2 bonded domains and 0 non-bonded domains. It's going to look like this guy right here. And the molecular geometry has the same name because there's only one member of the family right here called linear. An example would be our carbon dioxide. So around the carbon atom, we have a bond angle here of 180 degrees, and then we have a bond angle here of 180 degrees. So that is the first molecular geometry, linear, coming from the family of electron domain geometry called linear. Our next family is where there are 3 electron domains above the atom, and it has 2 members to the family. So the overall family is called Trigonal Planar. Has 3 total electron domains, and if we have 3 bonded and 0 non-bonded, then we get the molecular geometry called Trigonal Planar. And a good example of that one would be our BF3 molecule that we learned about back in chapter 8. That was an exception to the octet rule, where boron breaks the octet rule. And this one right here would have 120 degree bond angles because it's the farthest that those fluorines could get from one another. Well, inside the trigonal planar electron domain geometry family, if we have two bonded and one non-bonded, now we have a shape that's called bent. And an example of this would be our NO2 minus polyatomic ion. So NO2 ends up looking like this. And then an unshared pair right here. So we have one bonded domain, two bonded domains, and a non-bonded domain right here. So 2 and 1 ends up being a bent molecular geometry. I think I'm supposed to put a minus sign out here and put it in brackets, but it doesn't quite fit. Alright, 4 electron domains. This electron domain geometry is called tetrahedral. Tetrahedral has 4 and 0 in the main, like, basic member of the family, and that one would be called tetrahedron. Tetrahedral. And an example of this would be methane. So carbon with 4 hydrogens around it. And you can see in the textbook they draw it like they should right here. Notice how they've got the wedge coming out of the book, the dash is going back into the paper, and then these two are orientated to be in the same plane as the paper. Alright, then there's 3 and 1, so 3 bonded, 1 non-bonded. And this is called Trigonal Pyramidal, Trigonal Pyramidal, and this would be with 3 bonded, 1 non-bonded domain of electron, and a good example of that is ammonia, so NH3. And let's see if we can draw it like they did. N with 1 in the plane of the paper, and then a wedge coming out of the paper at us right here, and then a dash part going back into the paper. And our bond angle right here would be reduced right here. Our bond angle would be reduced, and that ends up being a bond angle of about 107 degrees. Whereas back up here in the tetrahedral, remember the bond angle was 109.5. Let's see, we got the 120, the 110. In this bent right here, the bond angle is reduced just a little bit back here in this bent one. It's not 120 anymore. I think it goes down to about 114 or so. That's kind of an approximate number right there. And let's see, then in tetrahedral we have 2 bonded, 2 non-bonded, and this one's called bent. And the best example of this in the world is water, where we have oxygen, 2 unshared pairs of electrons, a hydrogen that comes out of the paper at us like this, and then a hydrogen that goes back into the paper like this. And this bond angle between hydrogen, oxygen, hydrogen ends up being 104.5 degrees. 104.5. So that takes care of 3 families: the 2 electron domain, the 3 electron domain, and the 4 electron domain. And now we get into the little bit stranger ones. These ones have 5 electron domains, and this comes from the family that's called Trigonal Bipyramidal. And if we have 5 electron domains right here and 0 non-bonded, 5 bonded domains, 0 non-bonded domains, this one is called trigonal bipyramidal. Example of that is PCl5. And we actually do this structure back in chapter 8. You can see it right here. And in this, we've got bond angles of 90 degrees and 120 degrees. So right around here in this equatorial domain, we have 120 degrees between those guys. And right here, we have 90 degree electron domains on the top and the bottom. All right. Next one right here is 4 bonded, 1 non-bonded, and this one is called seesaw. And seesaw, example of that is SF4. And you can see the example right here in the textbook where we've got 1 non-bonded domain coming off of that equatorial domain. Notice how it pulls off of the middle. It doesn't pull off the top or the bottom. So now we have 90 degrees on the top and the bottom bond angles. And then these guys actually get squished together just a little bit more. So a little bit less than 120. So a little bit less than 120 degrees for the bond angle between this fluorine, this sulfur, and this fluorine right here. They get squished together a little bit by the non-bonded domains. The next one would be 3 bonded, 2 non-bonded, and this is called T-shaped. And in T-shaped, a good example of that guy would be ClF3. And in this one, we end up with only 90-degree bond angles because we've got these 2 unshared pairs of electrons in the equatorial domain. So 90 degree only. And then the last one is 2 bonded, 3 non-bonded, and this one's called linear. And the linear one right here, example is XEF2. And if I remember right, we drew this guy, whoops, I'm sorry, 180 degree bond angle because it's linear. We drew this guy in an example problem in Chapter 8. So that's the 5 family right here, 5 things. 5 is 5 bonded, 5 not, 4 bonded, 1 not, 3 bonded, 2 not, 2 bonded, 3 not, and those are all the molecular geometries that come from the Trigonal Bipyramidal family. All right, last family is where we have 6 electron domains, and 6 bonded, 0 non-bonded is called Octahedral. The family, of course, is called Octahedral as well. You'll notice that the family's name is always the same as a fully bonded set of domains. So 5 and 0, 4 and 0, same name, 3 and 0, same name, 2 doesn't have a choice. And an example of this would be SF6, sulfur hexafluoride, and this ends up having 90 degree bond angles everywhere. All right, the second member of the family is 5 bonded, 1 non-bonded, and this is called square pyramidal or square pyramid. And an example of this one is BRF5. And with this non-bonded electron pair, it actually kind of shoves these guys a little bit upward. Not a lot, but a little bit. And we just say approximately 90 degrees because we don't become quite as concerned about it. Although this is going to cause an uneven electron distribution throughout this molecule. Keep that in mind for next time. And then we've got 4 bonded, 2 non-bonded, and this one's called square planar. Because if you notice, all the bonded electron domains are in the same plane right there. And the example of that is XEF4, 90 degree bond angles for that guy. So if you look down the middle right here, the molecular geometries, those are the ones that you need to know. Those are the ones that you need to be able to identify. So find out how many bonded, how many non-bonded domains, and then the name of the molecular geometry. Here is the remember all: linear, love, trigonal planar, to, be, bent, love to be, T for tetrahedral, the, trigonal pyramidal, so play, and then B, boy. Love to be the playboy. That's a good way to remember these guys right here. And then trigonal bipyramidal is T, S, T, seesaw and T-shaped. So test, spelled wrong. And the reason you spelled it wrong is because L-O-S-S. It was a test loss. So love to be the playboy, test loss. Memorize them up. Know your bonded and your non-bonded domains, and you'll be golden for the rest of your chemistry career.